Any questions on anything? All right. No questions. All right. No homework over Thanksgiving break. It's a rule I have from my days as a student. I used to want to kill the professor who gave me homework over a holiday. So, but there will be homework when you return. Right? Life isn't perfect. Okay. So let's just do a very brief review of the practical side. Okay, so the way networks are generally constructed, just to sort of bring you up to speed on what we've done so far. You've usually got a local area network, okay, a bunch of devices hooked up to LAN. Yeah, I guess it's still this way. Okay, hooked together with some switches. However, okay, like so. And generally, when these devices communicate, they communicate at the data link layer. Devices on the same LAN use data link layer to communicate. Okay, so you can think of this as Columbia's campus, and maybe Columbia's campus is too complicated. Maybe this is the CS department. The machines in the CS department speak to one another. There is some interaction with the network layer, but really you can think of it mostly as interaction on the data link layer. Okay, there's really routers do very little. Okay, and then I go this way. You have another LAN, maybe some devices, and then sometimes you'll have what's called well, not sometimes, almost always these days. This is a router. Okay, and it connects the LAN to the wide area network. Okay, and then there's a bunch of routers. Okay, with all sorts of paths going through all sorts of these days, different companies implement these different routers. So you got Sprint, AT&T, Verizon. They all off backbone wide area network services. And then you connect to other LANs elsewhere. Okay, so here, sort of inside this region is where we're using the spanning tree algorithm. Okay, and to get from one LAN to another LAN is where we use the actual shortest path tree algorithms to find the path that would take us from this LAN, from a device on this LAN to a device on another LAN far away. Okay? And this course, we're not really going to get into the details of how the protocols interact or what the packet headers look like or things of that sort. Okay, but that's the basic idea. The spanning tree stuff that we did, where you turn on and off switches, that's done within a local LAN. And then the shortest path algorithms, like Dijkstra's or Bellman-Ford / distance vector, those are used to figure out the paths to get from point A to point B. And Professor Mishra last time covered trees, which uses longest prefix match routing, and that's just how the router stores the information about where to go for the next hop. Okay, after you've run Bellman-Ford, you've computed where all your destinations should be. That's a nice, concise way to condense the information. And the fact that you use IP addresses for distance locations means that distant locations will have very similar addresses, means that they'll have very similar prefixes, means it's easy to compress the identifiers. All right? So that's why IP addresses are useful in the wide area at the network layer, and we're really doing things in a local neighborhood, we're not too worried about the need to compress the storage of all the addresses. There's only a relatively small number of addresses. We can keep them in a simple list, so we can just use data link layer MAC identifiers. Okay? Okay, so we've looked at routers from the sense of control. How do they decide where to route? How do they have to decide where to route? Okay, there's also a data aspect to a router. How to handle packet arrivals. And this is what we're going to focus on for the next lecture and maybe even the one after that. So let me introduce the notion of a flow. A flow is a series of packets grouped together under a common theme, purpose, etc. Okay, so for instance, if this is your computer, this is the server, and you are communicating with that server, I don't know, you're downloading a movie from the server, okay? Then the set of packets involved in download can be considered a flow. Okay, flow is actually a somewhat abstract concept. A lot of times there's arguments over should you consider a flow. I mean, suppose you're downloading two movies. Should that be considered two flows or one flow? What if it's Jaws 1 and Jaws 2? Or, I guess, wrong generation. Matrix 1 and Matrix 2, right? When you're downloading them both at the same time, is that one flow or two flows? It's really arbitrary. We can call it any way we want. And for our purposes, what we're going to be looking at is we're going to be looking at a router. Okay, and there's going to be flows going through this router, more than one. So flow 1, flow 2. Okay, and this router has to process these packets from these flows. In a fair manner. And the question is, what is fair? Okay? So here's another way that those of us in the modeling world like to look at this. Have I drawn this picture before of a queuing system? I may not have. This is a queuing system. Okay, this is the buffer. This is the processor. Okay, and packets come into the buffer. Packets from the various flows, so I can number them. Flow 1, flow 2, flow 3. 1, 3, flow 1. And then this processor can process one packet at a time. In the context context of what we're doing, it's going to look at the packet, look at its address, and look at its Bellman forward table to figure out where to forward the packet and then forward it. Okay, that takes time. So you can only do one packet at a time. Okay. And identifying which flow the packet belongs to is a much quicker operation than actually determining where to forward the packet onto, right? I mean, you have to walk down this tree to figure out where to forward it onto. There may be some other processing you have to do as well for that packet. In any case, the question becomes, how do we fairly process these packets? So, for instance, consider the following. Suppose flow 1 is somebody using IP telephony. Okay, and suppose they send a packet every 0.1 seconds. Okay, so wants to communicate with some destination. Here's somebody on the other end, also on their IP telephone. Okay, it happens to be passing through this router over here, among others. I just drew the one router. Okay, and at the same time, we didn't even finish drawing this person. You got flow 2 is some machine downloading a movie, okay, from some server. Okay, going to the same router. And the packets are coming in fast and furious. Okay, so this thing is sending tons of packets. Okay, if you look at it from the perspective of the queuing system, draw it sideways. We've got these flow 1 packets, nice spaced, making their way to our queuing system, and then flow 2 packets maybe coming in big bunches. They're coming in very, very fast. Okay, and flow 2 packets can clog the server, basically. Right? I mean, I want these flow 1 packets to go through and not get stuck, and then maybe there's so many 2 packets coming in that this router is getting overloaded with flow 2 packets, and it's deleting my flow 1 packets. Okay, so many flow 2 packets are slowing down flow 1's transmission. Okay, so what can the router do? Okay, suppose the router doesn't have to process the packets in order. Suppose it could process flow 1's packets before flow 2's packets, or move packets around. What are different queuing strategies? Okay, so that's what we're going to be looking at. Just get the right term. Yeah. So can people think of some possible variations for queuing disciplines? I mean, so again, suppose I have 2 flows coming in. What are some obvious, fair ways to do the processing of these flows? Yeah, George. First come, yeah, we call it first come, first serve, or FIFO. Or which is FCFS, which equals first in, first out. Okay, or FIFO. I mean, it makes sense. The first one in should get served first. Okay. Everybody see what's going on in this one? Got some router. And if packets come in the order, so this is time going this way. So if packets come in 1, 2, 2, 1, 1, 2, they just get processed in that order. 1 then 2, then 2, then 1, then 1, then 2. Okay, what's another possible queuing discipline? Okay, let me put it this way. Suppose I divide the class into 2 groups. Okay, and group 1 is going to work on homework questions together, and group 2 is going to work on homework questions together. And now I'm going to have office hours, and people can come in and ask questions. Okay, and suppose group 1's got a lot of questions in group 2. Okay, so I open my office hours, and group 1 keeps asking all these questions. Boom, 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 boom. And group 2 gets asked a question every once in a while, but we're running out of time in the office hours, and group 2 doesn't have enough time to ask, that many questions. I mean, wouldn't you feel unfairly treated in group 2? I mean, isn't first come, first served not really always fair? Isn't there another policy that might make more sense? Yeah, Patrick. Sorry?
I have 3 packets to give 25% of my time to one call, 75 of the other.
Okay. Well, actually, that's a more sophisticated queuing policy. We're going to get to that one later. But so that's, I mean, good. But let's look at more simple ones. Yeah. All 3. Yeah. Which we refer to as round robin. Okay, so I look at my queue, and I'll take a group 1 packet, or flow 1 packet, process it, and then I'll make sure to go to another flow 2, and take their packet, if one exists. So I'll sort of cycle my way around the sets of flows, and if anybody's got a packet available, I'll process it. And if some flow doesn't have a packet available, I just skip over that flow and move on to the next one. Okay, so in the context of office hours, suppose I have 5 groups. Group 1, do you have a question? They ask their question, I answer it. Then group 2, do you have a question? They ask their question, I answer it. Group 3, do you have a question? If they don't have a question, okay, move on. Group 4, do you have a question? Asked and answered. Back to group 1, 2, 3, 4. 1, 2, 3, 4. Okay, that's round robin. Okay. So I guess let me draw the picture. So in round robin, we go 1, 2, and then next would be 1, and then 2, and then 1, 2. Right? Just to make sure that the 1s, 2s alternate. And again, skip over any flow. Without a packet in the queue. Okay? You have a question? Or?
I mean that, for example, we have a 1 and then a 2. What if there's no more 2s left and there's just like, a 1 and then a 2 and there's no more 1s left. There's like 52.
Right. No, then you skip over the 1s and you go to 2s. So you go 1, 2. Are there any more 1s? No. Okay, then I'll go to the next 2. Process it. Are there any more 1s? No. Okay, I'll go to the 2.
So do you have like a global view of all the packets?
Yeah, you think of all the packets in your queue. You can see them all quickly. You can read their labels quickly that indicate which flow they're from. And a slight variant is each flow has a fixed processing stop. Okay, so processor is idle. When flow has no packets in queue. Okay, so for instance, I say at time t, I'll be processing packets from flow 1. At time plus 1, packets from flow 2, time t plus 2, from flow 3, and then I go back to flow 1. And if a flow doesn't have a packet to be processed, the processor just sits idle during that time quantity. Okay? You're wasting time, but so for instance, it depends what you're using this processing for. So a lot of times, so for instance at the MAC layer, to do collision resolution, what you can do is you can split each device and give it a specific time slot in which it's allowed to transmit. And if that device doesn't use its time slot, you don't want to sort of shift and complicate all the schedules. Or I could tell my office hours, group 1 and group 2. Group 1, you come at 10 o'clock. Group 2, 10:15. Group 1, 10:30. 2, 10:45. And this way, if you come, your group's all guaranteed processing when you arrive. You won't have to sit idly. Although I'll be sitting in my office alone a lot of the times if nobody has questions, which is not the case when I have office hours and there's no homework to give out. Right? Okay. Not that I mind. I have plenty of other work to do. So. Okay. Any other queuing disciplines? Yeah.
Priority.
Priority. Yeah. Right. I mean, I don't think priority needs any explanation. Suppose, well, example, process flow 1's packets. Before flow 2's. Right, so in that case, I would process, so here's priority, flow 1, and then I skip over these and process all the 1's, getting to the 2's. Right? Now, of course, I mean, this picture might be a little misleading because I may have my queue, and a flow 2 packet may come in, and I'll process all the flow 1 packets first, and then suppose no more flow 1 packets are available. Then I'll start processing that flow 2 packet. Later on, a flow 1 packet can arrive. So it's possible that a flow 1 packet will be processed after a flow 2 packet. Right. And actually, something we need to consider when we're talking about priority processing is the notion of preemption. A queuing system may or may not abort a current job of lower priority to start processing one of high priority. To immediately start processing. Start processing one of higher priority. Right, so suppose I have, again, two groups of students, and I say group 1 gets higher priority. So before letting group 2 ask any questions, I always ask, are there any group 1 students with questions? And if there are, then I'll answer those questions first. And suppose group 1 has no questions to ask, and now somebody in group 2 asks a question, and I start to answer it. And in the middle of the answer, somebody in group 1 says, I have a question. If it's a preemptive policy, I'll immediately stop answering the group 2 question and work on the group 1 question. If it's not preemptive, I'll finish the group 2 question before going to the group 1 question. But every time we're done answering a question, I'll always go to the group 1 questions first. Work on those questions first. Preemption is whether or not I stop an answer in the middle. Okay, so if I have a packet in the queuing system that I'm processing from flow 2, the flow 1 packet arrives and flow 1 has higher priority, under a preemptive strategy, I'll put the flow 2 packet aside for a minute and process the flow 1 packet, and a non-preemptive, I'll finish processing that flow 2 packet, and then the next flow 1 packet has priority to the queue once it empties out. Okay? All right. So those are the basic queuing disciplines. Can anybody think of anything else? I'll give you a hint. Suppose I'm answering questions for 1 in group 2, and someone from group 1 shows up a half hour earlier than someone from group 2. And suppose I use one of these policies. Let's not use priority. Let's assume group 1 and group 2 are equally important. How does that change the fairness of the process? Suppose I use round robin. Okay, I've been answering group 1's questions for an hour, and there's 15 minutes left in my office hours, and someone from group 2 shows up. I'm using round robin. Why would someone from group 2 perhaps not think that's fair? Okay, let me give you an example. If you've had a sibling, maybe you'll understand this one. Right? Suppose mommy's been giving your brother attention for the past hour, and she's going to have to leave for work in 15 minutes, and now you want to show her something that you've done, and she's sort of sharing the time between you and your brother. Why is that not fair?
She's already spent an hour.
Yeah, she's already spent an hour with your brother, right? So really, she should devote more of this time now to you. Right? Fair. Okay, so for instance, in a networking setting, suppose you've got flow 1, and it's been sending packets. So again, let's do time in this direction. Okay, so it's been sending all these packets, and they've been getting processed without a conflict in flow 2. Okay, now flow 2 wants to send some packets. So here's flow 1's packets going to the router in that time. And then flow 2 starts sending at some point in time. Okay? If you do FIFO or round robin, okay, then flow 2 is in some sense unfairly penalized for starting late. Right? I mean, flow 1 was able to get all this information across simply because flow 2 had nothing to send at that time. Why should flow 2, flow 1 got all this extra bandwidth. Why should flow 2 not be given some credit for that? And on the other hand, suppose flow 1. Well, let's not get there first. So how could you implement this sort of procedure? So we're going to do it. I'm going to call it virtual clock, even though virtual clock really describes something slightly different. But for the purposes of this class, we're going to refer to this as virtual clock. Okay, each flow maintains a counter. Which we will also call a clock, or a virtual clock. That is incremented every time a packet is processed. shouldn't say each flow. A router maintains a counter for each flow that is incremented each time that flow's packet is processed. Okay? Each flow whose counter is smaller is given higher priority. Okay? So I've got two flows. They've got these counters. Some flows counter is smaller than the other. Okay, if I have packets from both flows sitting in the queue, I'll process packets from the flow with the smaller counter. Okay? At some point the counters may equalize, at which point the packet I process next, the decision is arbitrary. And that'll increase that flow's counter, and then I'll have to process the other flow. I'll process its packets next. Okay? So for instance, let's see. So here, let's have flow 1, flow 2. Counter 1 and counter 2. Okay, let's say the counters start off at 6 and 8. Okay, and let's say these are when the packets arrive. So I'll put an X wherever a packet arrives, and time is going down. Okay, so flow 2 has a packet arriving. So let's say, and let's, sorry, make one more column. This is the queue, and I'm going to draw a packet being processed like so. So this is when this packet's being processed. Okay, it's being processed in the queue at that time. And since flow 2 is having a packet being processed during this time, the flow counter is incremented and it goes to 9. Okay? And now it's done at this point in time, and these two packets are sitting in the queue. Right? Well, flow 1 has smaller counter, so this packet is processed next. Okay? So flow 1's counter is incremented. Now at this point in time, when it's done, we've got this packet, this packet, this packet, and this packet all sitting in the queue. But flow 1's counter is smaller, right? So again, flow 1's packet is processed. And the counter is incremented. And same thing once again. At this point in time, well, let's say it finishes very quickly. Let's say it finishes there. Okay, so let's get rid of that. Sorry. So now flow 1 still has a smaller counter, but it has no packets in the queue. So flow 2's packet gets processed next. Okay, so flow 2's counter gets incremented to 10. And then again, Flow 2 will only have one packet. Oh no, let's say we've gotten down here. So now flow 1 again has packets in the queue. So its packets will get processed next, and all of its packets will be processed. This will equalize the two counters, and now the decision of what to process next is arbitrary. So you can pick flow 1, but if you process something from flow 1, its counter is going to go up to 11. So the next time around, you're going to process something from flow 2. So its counter will go up to 11. Right? So you're going to start doing this round robin mechanism. Right? Yeah.
What kind of situation would you want to use this in? Because, like, with the example on the internet, why should you give priority to something that starts later? Like, understand what I'm asking?
Yeah. So let's look at an example of one. Well, suppose you have two applications. Okay, and one application sends its packets at regular intervals. Okay, and let's see if this is going to work. Yeah, and suppose the other one sends it in big bursts. Right? So, when it's at regular intervals, there's a time when the queue isn't utilized, right? And then suddenly this one's going to send it in a really big burst. And well, let me change a little bit. Suppose they both send lots and lots of packets. Okay, so this flow is really utilizing the system heavily, and this one, who just happens to be sending things in bursts, why should it be penalized by this guy who's using it heavily all the time? Right? When I send my small burst, that burst is very important to me. Why don't you just let it through? Why don't you put this guy aside for a minute? I mean, he's been using the queue the whole time, and it's not fair. I just want it for the short instant of time. So, like the student who comes in with just 3 questions, and I've got a student who's been in my office for the whole day. I mean, is it fair that I make the two of you round robin while you just want to be there for like 10 minutes? So it's sort of this periodic nature that really makes it an issue. Okay? Yeah, Emil.
Is there a queue in this one that says, oh, take a flow with the most packets left or least packets left?
You generally don't know how many packets are remaining in a flow. I mean, the assumption is that you know how many you've seen already, but you don't know how many are coming. Ron.
Third column is better, so
Queue, yeah. I mean, it's just what's going on in the queue. What the queue is currently processing, right? So that's what those lines are supposed to indicate. It means that those are the start and finish times when that packet was processed in the queue. Yeah, Patrick.
Now, you had in the example there, you had one that's shooting out packets. Now, what if it was doing it all day? Let's say it's shooting, it was in the flow for a very long period of time.
Right.
And I come with a third flow that is also very continuous, and like a day later.
Uh-huh.
Now, the clock is going to be, thousands of packets. Would I then come along and say, okay, well, you're right. If 1,000 is 0, the process a day's worth, this day the first, the
perfect. This is exactly where we're heading next. Huh? Well, okay, so the situation that Patrick's concerned with is, suppose you've got a flow that's been processing all day, and then suddenly this new flow comes along with a whole bunch of packets to dump into the system. And the top flow's clock at this point might be 1,000,000. Okay, this new flow would basically starve out the old one. I mean, 1,000,000 packets are going to get processed, or a day's worth of packets are going to get processed before the first flow gets to transmit anything again, right? Using virtual clock. So that's the notion of fair queuing. And the extension of fair queuing to virtual clock is essentially there is a delta. There's a maximum value called the slack. That is permitted between two flows counters. Okay, so if I make the slack 10, what that says is you basically get 10 packets for free. So if you have two flows, and one flow has been sending packets all day, and the other flow comes late, that other flow should have a reserve of those 10 packets. So it can take control of the queue for 10 packets, and then after it gets 10 packets processed, the two counters will be equalized. Okay, so you're basically putting a bound on the benefit that you get by not waiting. The benefit that you get by not transmitting. When you're not transmitting, right, the other flow's counters are growing, and by keeping your counter small, you're basically increasing your priority for a period of time. And fair queuing, there's just a maximum value delta on how much you can build up. So another way to put it is this way. A modification to virtual clock. Okay. When packet is processed from flow I, flow I's counter is incremented. Okay, and let C sub j equal flow j's counter. Okay, we've just incremented flow i's counter. Okay, then set Cj equals the max of Ci minus delta Cj for all j. Okay, so I've just incremented counter I. Okay, after doing that, what I want to do is I want to say every other flow can get this slack of at most delta. They get delta packets for free. So after I've incremented my clock by I, okay, I look at their counter, and if their counter is more than delta less than flow i's counter, I bring it up to be equal to delta less than flow i's counter. Okay, this has the desired effect. I'm going to try and draw out an example. Okay, so let's just sort of look at this, and let's just put a lot of packets. let's now draw counter 1. Well, okay, here's time, and here's the counter value. Okay, so let's say flow 1 is processed continually, basically. It'll be processed along with flow 2, so its counter is going to grow like this up until this point in time, and then it's going to be the only flow being processed. Its counter is going to still increase, and then flow 2 starts sending packets again. Okay, what happens to flow 2's clock? Flow 2's clock is also going to grow similar to flow 1's, right? And then at this point, flow 2 isn't sending any more packets, so its clock is going to stop. It's going to stay constant. But at some point, the gap between flow 1 and flow 2's clock is going to grow to be delta. Okay, and then the rule is when that happens, then even though flow 2 is not processing any packets, its clock is increased along with flow 1's clock to keep that gap at delta. Okay, so when we get to this point in time, when flow 2 is again sending packets, okay, then what's going to happen is flow 2's packets are going to still be processed, flow 1's are going to stop because its clock is bigger, but just for a much shorter period of time until their clocks are again equal, and then once again both packets will be processed. Okay? If we didn't have this delta, then flow 2's clock would have just sat flat, and at this point in time, flow 2 would have grabbed hold of the router or the queue, and it would have just set it to itself until the two clocks again equalized. So all that this slack did was to ensure that flow 2, by stopping the send, only got a limited advantage. Right, so if you so you could set delta such that it would give the flow, 5 seconds worth of advantage. So even if flow 1 was transmitting all day, flow 2 would come in and would only hog up the queue for 5 seconds, and then once again you'd trade back and forth. Any questions on any of these? One last thing we can do is so we've got this notion of priority. What we looked at was strict priority. Okay, you can also have non-strict priorities. Using weights. Okay, so suppose you assign weights to each flow. If flow i's weight is Wi, and flow j's weight is Wj, then fair means that for every W sub I packets processed for flow I, Wj packets should be processed for flow J. Okay, does everybody get the idea? I mean, suppose W1 is 1 and W2 is 2. What's that saying? What that's saying is right there are the packets. Every time I process a flow 1 packet, okay, I then want to follow up by processing 2 flow 2 packets. Okay? Take another flow 1 packet, take another 2 flow 2 packets. Take another flow 1 packet, another 2 flow 2 packets. Another flow 1 packet, whoop, another 2 flow 2, etc. Right? And if I made W1 equal to 3, W2 equals 5, again, same thing. Every time I take 3 of these, now what am I doing? Right, 3 of these, followed by 5 of these. Right, and again, followed by 3 of these, followed by the next 5 of these. Right, followed by the next 3 of these, etc. Okay, just asymptotically over the long term, you know, if I processed 3n packets from flow 1, I want to have processed around 5n packets from flow 2. Okay, so suppose I wanted to do this using a round robin scheduling. So let's look at weighted round robin. Okay, how do you set up the schedule? Given a set of flows, suppose F1 to Fn with weights W1 to Wn, and just for simplicity, let's assume that the weights are all integer valued. Okay. How would you set up your round robin scheduler? So that it achieves the right result asymptotically. I don't care about in the short term, but just asymptotically. Yeah, Ron. Yeah. Okay, so good observation. Flow I should get a fraction Wi, the sum of Wj, j equals 1 to n, of the slots. Okay, that's a very important observation. Right? I mean, if you did this, take the example with 3 and 5. The sum over both weights would be 8. So I'm giving 3/8 of the slots to flow 1 and 5/8 of the slots to flow 2, and then it has a proportion that I wanted, right? That's for every 3 packets processed for flow 1, I process 5 for flow 2. Right? So how would you go about implementing this? What you do is you create a schedule with this number of slots. Right? Give Wi of those slots flow I. Right? So I'll create 8 slots. I'll say the first 3 are for flow 1, and the last 5 are for flow 2. And by doing so, I'll have implemented this weighting ratio using round robin. Right? Yeah, Patrick.
And this would then give the empty slots to close become packets, or?
So what you do with empty slots, yeah, obviously if flow 5 stopped sending, right, the 3 to 5 ratio wouldn't hold anymore. It's only when both have stuff to send you want to maintain this ratio. So yeah, so okay, so think of it. Suppose I've got 2 students, and I want to say, for this student, for every 3 questions you ask, this other student's going to be allowed to ask 5 questions. Okay, and then I'll give what I basically do is I'll create a schedule. I'll go, question. All right, so I go to the first one. Maybe they've got 3 questions. Answer it. Maybe the next student, even though I've given them 5 slots, they only have 2 questions. So I'll answer those 2. If they've got nothing else, I'll go back to this one and answer the 3 questions. Okay, or you can make a schedule more intricate, where I go, 1, 2, 1, 2, 1, 1, 2, 1, 2, 1. Sorry, we've got just to match with this. 2, 1, 2, 1, 2, 1, 2. 1, 2, 3, 4, 2. Okay, and I can just repeat this over and over again. And so I'll just follow this schedule, and if I get to any slot and that flow doesn't have a question to ask, I'll just skip over to the next one. So when they've both got packets to be processed, when they've both got packets to be processed, you'll have the nice 5-3 ratio. If something doesn't, the ratio doesn't hold, but that's okay. The point is when both flows have packets waiting in the queue, this will process it at a 5-3 ratio. Okay? Whether or not you could also leave the slot empty is the other option. You can do it either way. It still holds. Yeah. Gary?
Yeah. Would you ever want to set priorities on the flows within the WJ slots?
Use priority somehow?
Yeah, I mean, you have 3 flows, and you set one of the flows to have priority 1, one of the flows to have priority 2, one of the flows to have priority 3. So you would process all the priority 1 packets first, and then priority 2 packets, priority 3 packets. Would you ever want to do that?
I've never really thought about that.
I mean, as opposed to how would you order them?
Oh, so I mean, usually what you do is if you're going to do a round robin sort of approach, and the packet who's supposed to be processed at that point in time isn't there, you just go ahead on the schedule to the next one. So you don't prioritize among flows other than through the use of the schedule. Okay, I guess you could. I've just never seen that done. Where you say if flow 2, if you have 3 flows and flow 2 isn't available for its slot, we'll give it to flow 1 with priority over flow 3. I mean, it's sort of mixing 2 different ideas. So you could certainly implement it, but I don't know what sort of property it would give you that would be that much more desirable than just skipping ahead on the schedule. Because the schedule, even if flow 2 got nothing to send, if you maintain the schedule, so suppose there's a 3rd flow. W1 is 3, W2 is 5, W3 is 7. Okay? Even if there are no flow 2 packets, okay, if you're skipping ahead on the schedule, this will still hold the 3 to 7 ratio. Right? I mean, I'll just skip over, if flow 2 isn't sending any packets, we're basically just skipping over slots. And so in that system, there will be 10 slots that are used, and 3 of them will still belong to W1, 7 of them will still belong to W3. So it will still maintain the ratio that way. Whereas if you do something funny with the priorities, like you were suggesting, you would lose that ratio, just because some flow dropped out. So, yeah, Patrick.
Real world stuff. Who sets the priorities? Does
In the real world?
the router? Does the
it's usually the ISP. And I'm not actually sure how frequently these priorities are used, but I mean, round robin really isn't very frequently used. So let's look at weighted fair queuing, because that is a system that's commonly used. Okay, or virtual clock. Let's consider virtual clock first. So how to implement a weighted virtual fair clock? Virtual clock. Weighted virtual clock. What would you do? Again, the idea is you've got this counting mechanism, but when both flows are sending packets at an equal rate, when the queue is filled up, for every W sub I packets processed for flow I, WJ packets should be processed for flow J. How would you maintain this relative ratio in the virtual clocking mechanism?
Yeah, you would have to reset the clock after each WJ.
Okay, well, suppose I didn't want to reset the clock. Is there a way to do it without resetting the clock? Patrick?
Have a different delta for every flow.
Sorry, right now, I use the delta to represent slack. I'm not sure what you mean by delta. So virtual clock had no delta, but there is something you do different for every flow. So that was something like that.
Increment its counter differently?
Increment its counter differently. So how do you increment the counter? Increment the counter by a weight. Right.
Everyone's going to get incremented 1, but it takes 3 packets. If the weight is 3 for 1, it takes 3 packets to increment that by 1. While another packet. So based on your weight, that's how many packets it takes incremented by 1.
So in other words, you increment the counter by 1 over your weight. Yeah. Increment Fi's counter by 1 over Wi for each packet. Right? So basically, flow I needs to have Wi's counter to be incremented by 1. And flow J will need WJ packets to be processed for its counter to be increased by 1. So if you think about what's happening, in order for basically virtual clock is going to keep the counters increasing at the same rate. Right? The flow whose counter goes higher, its priority is reduced so the other flow will, its packets will be processed. So over a long period of time, both counters will be the same. And if you're incrementing them in this fashion, obviously flow I will have, if flow I's counter grew by S, then S times Wi packets were processed, right? Because each packet increased the counter by only 1 over W sub I. So if the counter grew by S, you must have had S times Wi packets, right? And if flow J's counter grew by S, then S times WJ packets were processed. Right? So think about what the system is doing. At some time t, let's say the counters are equal for these two flows. And whenever one flow's counter goes ahead, the other flow gets priority. So over a long period of time, the counters are going to stay equal. They're both going to grow, but they're going to stay equal. And so what happens at a later point in time, both counters have increased by S, So flow I has had S times WI packets processed. Flow J has had S times WJ packets processed. It's the appropriate ratio, right? For every WI packet processed for flow I, WJ packets have been processed for flow J. Right? And the last thing to do is to extend this to fair queuing. So weighted fair queuing. What should the slack look like? Okay, we really have a choice here. You can have a fixed slack of delta. Right? Which would say that flows with very high weight get more slack in terms of raw number of packets. Right? Because a flow with very high weight, what I'm saying is if we have this fixed delta, then if I again apply the rule that C sub j has to be the max of its current value and of C sub I minus delta. And I've got this fixed delta, then if flow J just stops transmitting, and so its clock falls behind the other clocks by delta, it's going to get to send delta times W sub j packets in order for the clock to equalize. Right? So flows with very W sub j, they're going to be allowed to send a lot more packets until the two clocks equalize. Or we could set the slack to what? Suppose we wanted to give every flow the same number of packets we process. Suppose we wanted to allow each flow to have exactly delta packets be processed. What would we set the slack to? Delta over its weight. Okay, so Cj would now be the max of Cj and Ci minus delta over Wj. Right, so Cj will be at most delta over Wj behind any other clock. So in order to catch up, it will need, sorry? Oh. Well, here. Okay? So you fall behind by at most an amount delta over W sub j. How many packets does that allow flow j to send such that its clock will catch up with flow i's? Exactly delta, right? Because each packet transmission increases the clock by 1 over W sub j. Okay? Any questions? So next week, vacation for the rest of the week from the class. And on Monday, where we pick up again, we'll start modeling these using some Markov models. All right? Happy Thanksgiving.